The next topic I want to talk about is called media. Media is the material through which signals travel in networks and in communication. That's what we deal with. And again, I expect that you have done this before. Just going over for those who have not done it. And it's a revision for some of you, but there'll be a question on media in the exam as well, or sub-question, not necessarily a question, but it's a topic that usually pops up in exams. So what do we mean by media? The media is the material that carries the signal. So we can have electric media, as in cables that carry electric signals, or we can have fiber optic cables that carry light signals, or we can have wireless communication where we send an electromagnetic signal. So just looking at cables. If you use a cable, normally cables take information from one point to another point, and they call it point-to-point communication or link-to-link communication. I mean, it's not a broadcast. You can never broadcast with a cable unless you connect. You must physically connect every device to that cable, or make sure that there's a connection. But it's not really. Its nature is not broadcasting. Its nature is point to point. And the connectivity of cables can also be classified into: is it a point-to-point or multi-point? I mean, is it a shared link? You can have maybe two machines and there's a link between them. And this, we can call this point-to-point. If there's another machine or device, it can be connected to either one of them or both. This is also point-to-point. So point-to-point definition is you have a link and you have one device on either end. And they can communicate using that link. And that link is dedicated to those devices. So this link here is dedicated to those two devices. So, for example, A wants to send a message to B and C. If it wants to send a message to C, it cannot send it to B in order to send it to C. No, if you have direct link, you can use it. If not, you cannot communicate. Let's say another machine here, and it's connected to A and C. It can communicate only, D can communicate with A and C. It can never communicate with B. This is called point-to-point communication. Now you can have multi-point, is where you have a link and it's connected to one machine, connected to another one, maybe connected to a third one, fourth one. Now, any machine that wants to send a message to another machine, say this machine wants to send a message to this machine, this message goes all the way to the end, both ends of the cable, everywhere, and it goes to every device. So you're actually kind of broadcasting within this network. So this is a multi-point link. The multi-point link is like just a shared link. Right. Now, what's the difference between point-to-point or multi-point? This one is shared. This is the main difference between them. Shared link, and this is dedicated. We asked you earlier on which one is better, to use shared links or dedicated links. And what do you think? Which one is better? Very good. Yes. Okay. It depends. For example, now I want quality of service. Like when you compare them, quality of service. Which one provides quality of service? Point-to-point or multi-point? Which one is better at quality of service? Yeah, the point-to-point is dedicated one, has a better quality of service. and this is lower. It's not, not as great, but yeah, it has some quality, but not as good as the point-to-point. Which one is more expensive? As you can see here, you can connect more machines, and therefore more machines can communicate, and that's cheaper. So cost is high here, which is a bad thing, an arrow pointing downward. And the cost, if it was shared, the cost would be low, which is a great thing. What about scaling? What's scaling in networking? What does it mean?
Having more nodes?
Yeah. Scaling is getting larger or smaller in general. So normally in networks, they only get bigger and bigger. So which one is easier to increase in size? The multi-point or the point-to-point? Normally, the multi-point. Those local area networks that get connected with a shared link, they can go up to 200, 300 machines in a local area network. With those machines that need dedicated link, they cannot grow beyond 4 or 5 machines maximum. Like, it becomes very expensive. Then you need more cables here. And there's even a formula for these cables. How many lengths of cables do you want? How many pieces of wires do you need? That depends on the number of machines. So the number of cables equals the number of machines times the number of machines minus 1 divided by 2. So in this case, we have 1, 2, 3, 4 machines. 4 times 3 is 12, divided by 2 is 6. So in order to connect every device to every other device, you actually need 6 wires. How come here we only have 1, 2, 3, 4, 5? Well, here's the 6th one. In order to connect. Now, if you had 100 machines, with the multi-link, you have one cable, slightly longer, but you can connect as many computers to it as you want. But if we had 100 machines, you want to connect them using the point-to-point, it's going to be 100 times 99, which is almost 10,000, divided by 2, which is 5,000 pieces of cable, in order for every one of them to communicate with everyone else. So scaling, this is no, it doesn't scale. Very, very bad. And this is yes, it can scale, gets larger, and that's a big advantage. I just put in an arrow pointing upward means it's a good thing. If I said what are the advantages, just look at the arrows. This one can scale, this one has low cost, which is an advantage, but it has a problem, low quality of service. Why is the low quality of service? Because we have to share the link. And also, when you're sharing the link, if one machine transmits a signal and another machine transmits a signal at the same time, it's like us in one room, people in one room, and 2 people speak loud. So everybody can't hear each one of them. They can hear both, but they can't make out what they're saying. Only one person speaks or talks at any given time. Same in networks where the link is shared. But if the link is dedicated, this guy can talk to that one, while this one is talking to that one, there's no interference. There's no problem. So if 2 on this network speak at the same time, nobody will understand them, and we call that's in communication, that's called collision. So collisions in communication, if you ask what's a collision in communication, is when more than one machine transmit on the same channel. they transmit using the same frequency, then everybody hears the two of them, and nobody understands any of them, and we call that a collision. That's a problem in some networks, collisions. And to prevent collision in shared machines, you have to control who is allowed to talk. So you allow one machine you can transmit, and then another machine you can transmit, and when it finishes, another machine or so. But no two machines should start transmitting at the same time. Okay, we'll get back to this another time. There are other little properties. Robustness. Okay, collisions, they never happen here. We never, sorry, I'll just write here, never happen, and that's a big plus. And here, yes, possible. Yes, it's a down kind of that thing. It can happen only on shared links. I said robust. What's a robust system? Anybody knows what a robust system is? So these definitions you need to know eventually while going through a network or communication. Did I hear somebody? Hold on.
Even if one system fails, the rest will.
Okay, yeah, so even if there's part of the system fails, the system will continue to work. It will not collapse. Example, if this link breaks, will communication stop on this network? No. This guy, the rest of them can all communicate. Only those two cannot communicate. While if this link breaks on the shared network, that's the link that everybody can communicate through, and all communication stops. So again, P2P is yes, it's very robust, and this one is no. And yes, being robust is a big advantage, and no is being a disadvantage. See guys, that's why sometimes they're right. It's better to have this system robust point to point or multi-point. And never say, oh, definitely point to point is better. This depends on this. If you want quality of service, point to point is better. If you want cost, this one is better. This is going to be cheaper. Doesn't mean the cost is more or less. The cost, of course, is going to be low cost, and that's the advantage. Now, if you are scaling, if you're in a network that might change in size, grow, then it's definitely better to go for that one, for the downscale, and so on. So these are, and there, as you can see, there are many different factors. And in most choices in communication, there will always be many different factors. So be careful, don't give a straight answer in any of those selectively kind of options in technologies in general. But let's go back now to cabling. So again, we go back to media. Medium is the single kind of item that will carry information, but media in general is the plural for medium. So the first medium we'll talk about is the cable, and that's the twisted pair. It's the most used cable so far on local networks anyway, local area networks at this point. It wasn't always the most used one, but it's probably the oldest that's been around, and it's been developed for a while. It has been improved over the last 50 years. So twisted pair is simple, it's just a pair of wires. So you have a pair of wires, and that's normal. That was taken from the telephone system. A pair of metal wires, generally copper, because it delivers electricity, or it's a conductor to electricity. So, and usually we send a signal between two computers through a copper wire, or a pair of wires. Any communication started first, and this is the way it's still happening now in electrically connected devices, is that a current is flowing between those two machines that forms an electric circuit. It's just flowing all the time. They call it the carrier signal. It's just an electric current is flowing between two machines. That's how a machine knows my neighbor is alive, if it can sense this electric current. If it can't, if it sends it and the circuit is broken, the other machine is not on, then that circuit will be open, there'll be no electric circuit between them. So that's the first thing, you know, the first part of communications. That first we establish that there is a current flowing between those two machines. Normally, communication happens, and what we mean by communication is you move data from one place to another place. And all data on computers is all in ones and zeros, in binary. And this information is transferred. We actually never send ones and zeros. It's always the same electric signal is going. The only thing is that every electric signal has a number of properties. And it's either the voltage, and they call it the amplitude. So we change the strength of the signal or the level of voltage in that signal. So for example, if the electric signal that's flowing now between these two machines, either maybe 5 volt or 2 or 0 volt, just continuously going 0. But if we want to send ones and zeros, the two sides must agree. For example, we agree 5 volts means 1 minus 5 means 0. We both agree that. Then I start looking at my data here. I am the sender. And I see 1, 1, 0, 1, 0, 0, 0. That means bring up the voltage to plus 5. Leave it there for a certain length of time. You and I agree, the two devices agree, what's the length of time to represent a bit? Usually 1/1,000,000th of a second. But let's just say now for 1 second. So bring the voltage up for 1 second. This guy sees that, then he writes 1. Then leave it for another second. Then that means it's another 1. And then this guy, I can read 0, so I'm gonna drop my voltage to -5. So this guy senses the voltage went down. The good thing about voltage is that we can turn it up and down so easily and so fast. And we can also sense it so easily and so fast. And we can actually sense it 10 million times a second. So every second, we can bring it up and down 10 million times, and the receiver can actually sense it 10 million times and write in its memory, it's 1 or a 0, it's up or down. And that's how it goes. So then he says, oh, another 1, let me go up to +5, and then a 0 goes -5, and then another 0, -5, and then another 0, and so on. So that's how it actually works. This is called amplitude modulation. Modulation means changing. So you look at the bits, ones and zeros, you translate them into amplitude based on the agreed values between the sender and the receiver. Usually it's laid down in a protocol that you have no choice. It's 5 and 2.5, and that's it. Both must agree to that. There's another technique, and it's called frequency modulation. Frequency modulation is that, again, something else. Every electric signal has frequency. And frequency, anybody knows what's the definition of a frequency? Number of cycles per second. Electricity always generated in a cycle between plus and minus, because as generators rotate, current goes up and down, up and down. So it's always cycling between going up and down. Over time, it keeps going this way. If we introduce time into it. So the number of cycles per second, you can see them really slow or fluctuating fast. That's called frequency. We can change it as well. We can say, hey, for low frequencies or very high frequencies, for example, we can select 1, and another level can be higher or lower. For now, I'll just say, low frequency 0, 0, and then high frequencies represent 1, and then another one 0. So that's 0, 1, 1, 0, 0, 1, 0. Leave it low for another little while, and then high, and so on. So if I was the sender, I look and I represent 1100, I increase frequency between us, so the receiver can sense this high frequency and translate it right one in your memory. And then I slow it down, that means 0. And once we agree on those two values, that's how computers transfer data, by agreeing two different values.
What did you say the second the frequency modulation is called? Like that? Is there a name for that?
The what?
You said amplitude modulation, and then the second one is called?
This is frequency modulation. That's changing the frequency values to represent the data. So this is known as amplitude modulation. This is known as frequency modulation. There are a couple of other techniques. We don't need them right now. But what we need to know is how do actually twisted pair do the job, and how good do they do it? Now, there are a couple of things you need to know as well that are natural events that happen with electricity again. If you have an electric wire and you have a current flowing through it, an electric current flowing through it. For example, you have a device here, you have a bulb here, and you want to send electric current to light that light. The further the current travels, the more resistance it will face, and the weaker it will get. That's why they always, around the world, they have a problem transferring electricity from one place to another. If the place is far, you're going to lose more electricity by sending it over longer distances, until they find a better way. But for now, this is a natural occurrence, a natural thing that happens to electricity flowing through wires. Just like you swimming in a river in the opposite direction. You swim and the current is holding you back. So you might swim a little bit and then you get tired and then you can't go any further. That's exactly what happens to any electric current going through any material, usually conductor, any metal. Different metals will have different resistance, will offer different resistance to electricity. So they started mixing different metals together to find the one, or come up with something that will produce less resistance. Copper is probably one of the best conductors. It offers less resistance. But they found that if they add to it some other metals, they can come up with better material. Now, twisted pair were used in computer network. So any group of computers, you want to connect them with twisted pair. But they found that after a certain distance, the signal gets weaker and weaker and weaker to a point that it's no longer recognizable. And that distance, they refer to it as attenuation. Not the distance itself, but attenuation is the weakening of a signal. You start with fresh signal 5 volt, you send it over, it becomes 5, 4.5, 4, 3, the voltage is dropping to a point that is no longer recognizable by the receiver. So if the signal, the transmitter sends a new fresh signal that has 5 plus 5 and minus 5, after a few meters, it will break the edges. They're no longer sharp, they'll be a little bit cornery, and they no longer go up to plus 5, they go to plus 4 or 3, and then becomes like this, and then becomes just a straight line, no longer recognizable. So if I was a receiver, and I'm waiting and sensing the voltage, I'm no longer getting plus 5 and minus 5. I'm getting plus 1 and minus 1, maybe, or even less. Maybe plus 1 and minus 1, I still recognize it as 1 and 0. But it gets to a point where you know, this is what we mean by attenuation. So attenuation, every signal, whether it's electric or light or any form of signal or sound, the further it goes, the weaker it becomes. Like if you call somebody from here, they might hear you in 20 meters, 200 meters, they may not hear you. They might maybe hear a tiny bit any longer, and it becomes unrecognizable. So that's known as attenuation. So what's attenuation again? Can you remind me? What is attenuation?
When voltage through the wire starts going down because of the resistance.
Over the distance, yeah. So it's the weakening of a signal, not just the weakening of a signal. You're right, it's the weakening of a signal. That's not, you don't get any more. Over distance only, not for any other reason, only for traveling, moving, not for other reasons that could weaken a signal. The weakening of a signal over distance. And in twisted pair, when they started using twisted pair about 40, 50 years ago, the distance was 10 meters. So that's your maximum distance that you can send an electric signal with 5 voltage to a receiver that will receive it and understand or recognize it. They count 10 meters, which is not great. So they did use those twisted pair, and then they improved them a bit, and they used to call them, they created better wires, and they issued them again, but to differentiate them, they call them class B, or is it class 1, 2, 3, and up and 6, yeah. Class 1, class 2, 3, 4, and they kept improving it over the years. Every decade or so, they produced a better wire. Right now, they have class 6, and they actually, twisted pair now, have the range, or they have the attenuation of 100 meters. That's what you buy in the shop today. Is like if you go to any computer network and say, can I buy a computer twisted pair network cables? They give you the cables, and they have the range of 100 meters. Yeah?
That's what's commonly called Cat6 cable, right? We're not Cat6. On those lines?
Yeah, the Cat6. Yeah, exactly. Yeah, it's category, short for category. So they have categories 1, 2, 3. Category 6 is the best cable available now. Cat6E, I think. But you can't go and say, okay, can I have Cat7 or Cat5? Usually they say, no, that's what I have. After a while, they stop using the previous Cat when there's only one category. You might find Category 5, and they are cheaper ones now, because Category 6 just came out a couple of years ago. We still have plenty of Category 5. The Category 5 cables are available.
It's not true. I mean, it's not really true.
Oh.
Now it's like Cat7, Cat8.
All right.
Yeah.
There you are. So we have more people who are more up to date. Thank you. And do you know the range?
For the new ones?
Yeah.
No.
Okay. Category 6 is 100 meters. I'd imagine Category 7, they're either 100 or maybe they managed to bring it up to 120 or 130, maybe. We don't know. Okay, you can find out. Right. So this is twisted pair cable. Twisted pair cables are very cheap. Like Category 5 is probably 30 cents a meter or something like that. Maybe Category 6 is probably, I don't know, a euro. Do you know any price?
The price, but I think Cat6 is still the furthest. It's just that Cat7 and 8 have a higher bandwidth.
All right. Okay. So, and cables as well. Right. When you buy actually a network cable, instead of getting one pair, you actually get 4 pairs together in the same wire. So just in case you want to connect more machines, they have specific colors that are used. So hopefully you don't, when you connect one wire, you don't connect the wrong wire at the other end. Just identify it by color. And also, you need to connect them in a certain way between a computer and a router, or you connect the computer to a computer, or a switch to it. Anyway. But that's not really now what concerns us. What concerns us, again, is that cables, twisted pair cables, are reasonably of low cost if you want to buy them, to buy meter for meter. But not necessarily they're the cheapest thing to use. But we also know that they have attenuation. That means they have a limited. Everything has attenuation, but for this one, it's probably the smallest kind of type of cables that we'll be talking about, or media that we'll be talking about. What else? Now, anytime you send an electric current through a wire, there's a natural thing that happens, that wire generates a magnetic field around it. You don't see it, but a magnetic field is generated. If you bring a magnet beside it, or a compass pointing to the north, it will be actually pulled towards or turned away from the wire because of the magnetism. So there is a magnetic field is generated around any wire that carries electric current. That's actually, the current is moving. If the current stops, the magnetic stops as well. The magnetic field goes. And that's not a big problem. But from a security point of view, it is, because that magnetic field varies based on the current that flows through it. So if you're increasing the voltage or reducing it, or frequency, you'll start increasing the magnet or reducing it. And there are antennas, there are devices that, without actually touching the cable. The problem with twisted pair cables, if you have twisted pair cable running to the street, somebody in the street come up and strip it and tap it. That means get to their wire connected around it. And they get a copy or branch or tapping, they say, into their computer, and they can read all your information that's leaving. That's why we say, security is people outside. The moment it leaves your machine, it's no longer safe. Goes out in the street, they can pick it up. Sometimes over a window or under the ground, they dig it. Also, they can actually, even if you cover it with material, they can actually pick it up magnetically, because that magnetism that's created, you can actually pick it up with an antenna. There are specialized devices that are used to pick that information. Spies and countries, like especially if your organization has sensitive information, or is commercially is very important, or is manufacturing something, a new technology, and you're communicating with others, make sure or be certain that there'll be others who are trying to pick that information. And they'll pick it so easily, especially if it's radiating. So twisted pairs, they carry information, but they radiate. So like, here's what I am carrying. So they're easily picked up by, an antenna device or some devices that pick it up, connect it to your computer, and you can see all the information flowing, or store it and take it away. So they're not secure, basically. Why are they not secure? Because they radiate. The other reason why they're not secure, because anybody can come in, strip the cover on that twisted pair, connect their own wire, and strip it on this one, connect it, there it is, they have now tap. This is called tapping. So twisted pair can easily be tapped, and it radiates. So it has two security problems. Tapping can be a problem, but it can be an advantage. If we have a network in this room and we have 20 computers connected, and we need one more computer, we can just again tap it. So easy, strip that wire and make a connection and add another computer. So tapping can be an advantage, can be, if it's legal, done by the owner, the right person, then it's okay, it's great. You can use twisted pair and they're great for that. But tapping can be dangerous if you look at it from a security point of view.
What impact the signal by tapping?
Until it is detected, security people can tap. They might do it at night. It will affect the signal, but it will not be recognized, or at least maybe not till tomorrow for 12 hours. They can take tons of data in the meantime. So that's one technique. And the last thing is that it carries actually, I don't know, anybody knows how much data does it carry? It's used to carry 10 million bits per second, went up to 100, I think it went to gigabits now. So it can carry thousands of millions of bits per second. How many gigas will, again, it differs with the categories. Those categories, the higher the category, the more the data. Right, now that's twisted pair. Now let's get to the other wire, that's called fiber optic. fiber optic cables. There are other types of cables, but they're no longer in common use. They call them coaxial cables. We won't discuss them now, but I'll discuss the fiber optic cable. And this is the kind of thing you should have maybe done in a previous course, but I'm going over for general knowledge. The fiber optic cable is a cable made up of glass. It's manufactured out of glass, just a little thicker than a hair. So it's slightly thicker than a hair. It's a line of glass. And because glass is so fragile and not flexible, sometimes when they manufacture it, they put some pure form of plastic with it. So it gives it a little bit of flexibility. And the idea how information is transferred in glass is that you take your data from a computer, that's ones and zeros. Normally we send it in an electric signal, again, voltage or frequency or whatever it is. So what we do is we feed it into a light generator, like a laser or like a flashlight. So you have the data coming in electric, lights a light, and that light will shoot a light beam. So the light beam travels, goes into one end of the hair, travels, sometimes it hits the edge, it's reflected, it hits the edge, reflected back again, until it gets to the other end. Even if the wire is twisted, it will follow the wire. At the other end, it's met by a light-sensitive cell that you can generate. Normally, you can generate electricity from light. So these are the kind of light cells, and that one will convert that into electric, or there's already an electric signal. It will modify it based on that, and now you have into electric signal, and then convert it back into data ones and zeros. So this is the technique has been used since maybe, this is a later technique, but came into operation maybe back in the 70s and still going and going strong. So how good is that? One good thing about it, maybe I'll write those points that electricity does not radiate. So if I say radiation, I just want to compare between twisted pair and fiber optic. Twisted pair, yes, it radiates, and that's a very bad, sign. It's not good for security. Fiber optic light never radiates. It doesn't generate magnetic field. It doesn't generate anything. It's one light beam that travels through. It doesn't generate anything that can be picked so far. So no, it does not, and this is a big advantage. So it's secure. So immediately, fiber optic cables are a lot more secure than twisted pairs. You can't pick them up without actually doing something with them. You have to, but there's nothing that comes out of this wire. The other thing, tapping. How easily they can be tapped. Now, twisted pair, easy. And this one, no, it can never be tapped in situ. There's no technology, unless you say there is something new, that you can actually break a glass and connect it to another one and weld it back again. It won't work, it doesn't work. So far, there's no technology that can do it. The only way to add a device, even if you had your own machine, computers in a network connected with fiber optic cables and had 30 devices, you want to add one more, if you have no connection for it, you can't tap it. You have to replace the whole cable, throw it away, buy another one maybe that has 64 connections. Now what they sort of do is they have these ready multiplexers, a little box with one light, and there's 24 coming out of it, or 32 or 36, or 64 or 128. It allows you to connect more machines. But if you did not take that into consideration, you cannot tap it. Right, is that good or bad? Which one is better? The cable that can be tapped or the cable that cannot be tapped. Twisted pair can easily be tapped. Fiber optic cannot be tapped.
Depends on the machines.
Depends on what?
How many machines are being used?
Let's say 20 machines. What difference does it make? What do you think? Which one is better? You find the cables that can be tapped or not? That's better. It's a good answer, but it's not the right answer I was waiting for. It depends, are we talking about security or not? So if we are more concerned about security, which one is better? Twisted pair or fiber optic? Fiber optic, because it can never be tapped. You're relaxed. You know your data is not somebody gonna listen to it or take a connection to it, you know, by breaking that wire and connecting another extension. If we were thinking about just adding another machine, expanding in the company legally, well then twisted pairs are easier to do that. Not just easier, we can't do it with the other. Now, let's talk about something else. Something called bandwidth. I should have talked about this first. Bandwidth for now, it's the capacity of the channel, of this cable. What's the maximum capacity? And let me get back now to the frequency, but just to describe or explain to you what a bandwidth is, and then we get back to the differences between them. Remember earlier on, I said if there are two machines here that want to communicate through a wire, they must have two frequencies, for example. For example, you and I can agree, frequency 1 megahertz, 1 million cycles per second, and 1.5. What represents 1 and 1 0? We can exchange it. So there are two frequencies. So now I can transmit those two frequencies. Whatever, it doesn't look good, but here, there's. Now, two other users can be allocated to the same wire, but they can use any other different frequencies. And those two signals can actually travel on the same wire at the same time, electric wire, without any interference. They will not interfere with one another. They are able to do that. So now we can actually, in the meantime, I was talking about multiplexing. So we can send two signals or two different frequencies, so those two users can use. So if two users are allocated two frequencies to transfer their messages on a link or on a channel, then two other users, let's say A is talking to B, but then we have C talking to D. We have two other users here that can use same link, but use different frequencies. As long as the frequencies are different, we can actually transfer multiple signals that use different frequencies on the same channel without causing any interference, provided every two know what frequencies they use. They call this frequency multiplexing. So we can actually multiplex multiple signals into one wire, which is great. That means, hey, we have one twisted pair cable, one wire, and it's actually, you know, we can send as many signals as we want in it. But is that correct or not? We say, yeah, the frequencies that you can send, let's start from frequency 1 cycle per second. That's very low frequency. Can we send that? No. Some certain frequencies will not travel any further. And also, very, very high frequencies will not go on that cable or that wire that we have. So certain channels have certain capabilities to take bigger or smaller range of frequencies. So twisted pair, there's a limit. That, for example, if this is line of the frequencies that are available, small frequencies, and this is the largest frequency, that bit here is too high, cannot be used in twisted pair, and those low frequencies also are not suitable. So there is a range of frequencies, a usable range of frequencies for any material, any type of wire. And that range of usable frequency is known as the bandwidth. So what's the bandwidth? Is the range of usable frequencies that can be used on this cable. What does that mean? It means if you have a very big range, every 2 frequencies you can give them to some user, another 2 frequencies to another user. So we can have more multiplexing, with more communication on the same wire. So the twisted pair has, again, a limited bandwidth in the hundreds of millions, 100 million in total. So the bandwidth, there are actually 2 definitions, whichever one, in reality, just how many frequencies can you use? Imagine these are all frequencies. And remember something else, you can't say frequency 1 and then 2. They're too close to one another. They usually leave a gap between them. So if you allocate 2 frequencies to some users, you can't allocate exactly the next number in frequency to the next user. There has to be a gap between them so there will be no interference. We don't need to deal with that, but that puts a limit on how many frequencies you can transmit on the same cable simultaneously. So that's either that as a definition. So the definition of bandwidth is the range of usable frequencies. Or, okay, if we have, for example, if we have 200 frequencies or 500 frequencies we can use, pairs of frequencies. That means on each one of them, we can send data, bits. So bandwidth would also reflect the total amount of data you can transfer. Okay? So it's either the range of all the frequencies that we can use on that wire, or every pair of frequencies will allow us to transmit data between 2 machines. So what's the total number? A bandwidth can refer to the total amount of data which can be transferred. So whichever idea or definition you can use, that's fine. So that's something that we can also, that different media have they have different bandwidths. Twisted pair has the lowest of those bandwidths. So that's what the point earlier on I was writing here, comparing a twisted pair with fiber optic cable. This is very low, the bandwidth is very low. That means you can send very limited amount of data. On fiber optic cable, it's so large. It's the largest of any media that we know of. And that's, the technology is still growing. They haven't reached kind of the limits as such of how much fiber optic cable can transfer. Every few years, somebody comes up with a better switch that can actually fluctuate light in different frequencies, and they try it on fiber optic and it troubles. So far they haven't, so there's still a limitation of the switches that generate the frequencies rather than the fiber optic so far. So possibly right now, fiber optic wire can probably carry as much as 1,000 twisted pair wires can carry for one single wire. So that's the approximate range, or we compare the 2 of them. So what's left with is attenuation. So if you have a huge amount of data, for example, if you join a company tomorrow and they say to you, great, you're here now, here's a computer guy or a network guy, we're going to connect our computers in a network. Shall we use twisted pair or fiber optic cable? Which ones? Which cables we use? Electric or fiber optic? What would you recommend?
For what setting are you using? In what environment?
We got to a company, you got a job in a company, come and look after our network, they got you as the network guy. But they say, first job we want you to do, we have these 50 machines or 100 machines that are in our company, we're going to connect them into a local area network. Shall we use twisted pair or fiber optic cables? What would you recommend? Anybody? Fiber? Yeah, it's a good choice, but it's the wrong answer. What do you think? Twisted pair. That's another good answer, but it's the wrong answer as well. Be careful, guys, be careful. It depends on what. Security, let's say first thing, security. Hey, we were worried about security. Some people walk in and they try and maybe tap in our, what do you think? Our wires go over the roof and over the ceiling. Sometimes we hear people up there, so maybe we're where they might be tapping our information.
So for security fiber optic.
So for security reasons, you say, guys, if you're worried about security, go for fiber optics. Yeah, give me another.
Distance?
Distance, yeah. Attenuation. I didn't mention what the attenuation for the fiber optic. The twisted pair, I said it's about 100 meters. Right? After that, you need a repeater. You need to buy a device called a repeater that will send the signal for another 100 meters, and so on. And you might, your signal, you know, your network is a little bit bigger than 200 meters, then you get another repeater. But there is a maximum number of the number of repeaters you can use. But if there wasn't a maximum, you can have as many repeaters as you need. Now, anybody knows what the attenuation for fiber optic cables?
It's in the kilometers.
It's in kilometers, yeah. It's between 60 to 100 kilometers. So a fiber optic cable can carry a signal for 60 kilometers without having to need a repeater. So yes, if your company kind of expands into 2-3 kilometers, maybe.
Your repeater is like an injection of more energy, right? Or
No, that's probably an amplifier will inject more energy. If, you know, technically, the repeater will analyze the older signal and will generate a new signal based on that. For example, it receives, the signal should be +5 and -5. But to put it in a repeater, it probably reads +1 and -1. It says, oh, the +1 is at +5 and -1. So immediately converts the +1 to +5 and the -1 into -5.
But it runs on something.
Pardon?
It runs on power. No?
Yeah, it needs electric
So
power,
it
yeah.
doesn't need.
It needs some power. Oh, definitely. A repeater will need some power, yeah. Right. So fiber optic cables, they actually run up to 60 kilometers. Yeah, if you need, or 100, up to 100 kilometers. If the distance is longer than that, then you need a repeater, fiber optic repeater as well. It needs electric power as well. And the bandwidth, right, and so on. So these are the options that you need to think about. But there are other options. What happens if our campus has a lake in the middle and cables go in this water, in this, whatever we have, a river, or we're close to a sea and it's salty water, goes into salty water. Any ideas how would twisted pair or fiber optic will react? Rust, or, you know, getting rusty, and twisted pair is copper. It will rust immediately. It's very bad. It rusts. So it won't last for long. It won't last for a month. It will rust away. Fiber optic, it's okay. It never rusts. It's so. I'm going to say here the environment, not just the environment. Environment means water, salt, you know, humidity, things like that. Now, in fact, I don't know, did I mention the first twisted pair cable in Europe, across Europe? Did I mention it last week? No, we didn't talk about it. Okay, back before your times, guys, there used to be something, it's probably coming back again. There used to be something used to be known as the Cold War between the West and the East, right? And thus they were always worried. They're always mistrusting each other. They always think there's a war going to happen now, so we better get ready. And it's kind of Russia and America, maybe. But of course, NATO includes Europe as well, so Western part of Europe. So at the time, they were always racing in producing, you know, bigger military power. And it looks like in communication, the Americans and the Western Europe were kind of ahead of the Russians in communication through more satellites. They put more satellites upward and they can communicate directly, and they have cameras going around up in those satellites. And the Russians, they said, okay, they came up with an idea. They said, okay, in the case of war, first thing we'll do, we'll send one nuclear bomb, but not on America, but up in the air, over, the ocean. And what it'll do, it will blow away all these satellites. They'll disappear, and therefore we'll win this. There'll be no communication between America. This is true. This is real stuff that was happening. So the Americans and the Western Europeans, they said, okay, let's have a standby system of delivering data and communicating in case the satellites disappear. So they put an experimental project of laying down a fiber optic cable between Europe and America. And this happened in 1976. So a fiber optic cable started. The first cable was laid down from west of Ireland here, all the way to the eastern coast of America, in order to try it, and they started testing for telephone communication, and it worked. And it's been working ever since. This is almost 50 years now ago. And this cable is carrying right now 80% of the communication. Well, of course, they added more cables to it. But they're carrying 80% of the communication between Europe and America right now, all telephone communications, all TV channels and transmissions, and other forms of communication. So a fiber optic cable went down. Of course, it needs a repeater every 60 or 70 kilometers. So they actually have a box of a repeater that's connected by electric wire all the way to the end. And it works, and it hasn't stopped. And it's not corroded since then. And right now, fiber optic cables are laid down under the oceans, across all the continents, across all the oceans, connecting continents and different countries. And they carry possibly 80 or 90% of the communication around the world. But they haven't rusted, so luckily, they're not rusting away. And they're fast, and they have a huge bandwidth, which they mentioned there. And it looks like they're here to stay, and they do not radiate. Of course, you can still, put a bomb beside it and blow it, but they're hidden, hopefully, under the ocean, but they can be located.
Yeah, just two questions. The first one was, you said it was for like the phone lines, but I'm assuming it's also internet is going through it as well, right?
Yeah.
Okay, and the other question is, how do they deal with the multiplication?
Yeah, they have the repeaters. Okay, it's a different time for this, or different lecture, but let's say between America and Europe here, the cable's going down, the fiber optic cable, every 100 kilometers or so, you'll find a box unit, sealed unit, and it has the repeaters in there. And these repeaters are connected by electric power to it. Yeah.
But it's just that, like, how is that electric power connected? Seeing as we have, I'm just confused here.
They have, with the fiber optic cable, they have connectors.
Right.
They have a cable traveling all the way to here where it's sent. So they have a current at that point there that generates
It's
the
like
light.
5,000 kilometers, right? So
Yeah.
the amount of energy that the resistance, I'm assuming in the middle, power in the middle.
It's very little. Listen, the twisted pair cable that uses a lot of electricity, it uses 5 volts. It's minute, it's not huge. We're not now in an electronic or electrical engineering course, but now in the communication part. But by all means, find out how they are connected. But you can check on the net. You'll see that there are those repeaters repeated every certain distance to refresh the signal, the fiber optic signal. Now, the bandwidth is huge, and the distance is troubling. It doesn't radiate, and it doesn't rust away. There's something about twisted pair I forgot what I was going to mention. But so anyway, so which one is better? Again, It depends on the cost, for example, on the amount of data. So if, for example, the company is a video editing organization, like they get a lot of videos. The moment you hear videos in our communication, that means huge amount of data, a video, and it needs to be delivered at high speed in order to watch the good quality. But if our company just edit videos, transfer them between us, one to the other, then twisted cable will take a long time to transfer a video, so we do recommend fiber optic cables. But if our company deals with messages, short messages that can be exchanged, well, then maybe fiber optic cable will be too expensive, or not necessary, at least for the cost would not be very viable. So think of the cost and think of the other factors as well. So if something doesn't need high speed, doesn't need long distance, the quantity is small and doesn't need quality, a good quality of service, well, then go for twisted pair. Why pay a lot of money, so you have a lot of potential, but you're not going to be using it anyway. Now, let's get at the last form of communication, or the last medium that we have, and it's the satellite. So satellites, there are many forms of satellites, but we are more interested in one form of satellite. We call it the communication satellite. Communication satellite, a satellite is a device that receives information and retransmits it. So it's known as transceiver. So a receiver and a transmitter. That's all what satellites are. So the receiver and the transmitter, they need power as well. So most of them will have kind of, they can generate their own power from the sun. So they have these cells that will generate electricity. They also, the satellites, the way they operate, for example, a TV station here want to transmit through satellite, it will transmit its signal to the satellite. The signal is transmitted back immediately. So it's like a reflector, receive and transmit immediately, but when it transmits it back to the Earth, it will cover a large surface of the Earth. Like a satellite, maybe can cover the entire continent of Europe to transmit a signal. And there's so many satellites available, and anybody who wants to transmit anything to any location on Earth, you can do it. The satellites are there are companies that own them, and they're offering them for rent. So if you have maybe 10,000, 20,000 euros, you can transmit to Europe or to Ireland for an hour, if you like, a video or sound or whatever, radio signal or TV signal. The service is available on the internet. So these satellites, they rotate around Earth. Of course, Earth rotates, and these satellites also rotate. And they also rotate. Earth rotates around itself once every 24 hours. And all these satellites rotate around the equator. So if Earth is like that and the equator is here, all satellites are in a bigger circle or orbit where the equator is. So they are all on the same circle. They're not in different directions. I'm talking about our communication satellites. They're all in one big circle at a distance from Earth. Anybody knows how far they are from Earth?
300,000 kilometers?
Yeah, 300, around 300 and 365,000 kilometers. All of them are at that distance, and they're only at that distance that they will remain. And they all rotate at the same speed. Of course, they're doing much traveling at longitudinal speed. They're much faster because remember, they have to cover all this distance in the same time as a point on the surface of Earth will cover the full circle. That's every 24 hours. The circumference or the equator is about 24,000 kilometers. So any point on the equator rotates around, comes back to the same location in 24 hours. So you can work out how fast it is. But any point traveling, if you had somebody fixed outside Earth and watching it, the point will be traveling around 1,000 kilometers an hour normally, because every point. Like we are now, right now, rotating at approximately longitudinal distance 1,000 kilometers every hour. Now these will travel at a much faster rate, but still rotational speed or angular speed, they rotate one full revolution every 24 hours. And the reason is that when you transmit the signal to that satellite, the TV signal, they're received by the dish. You know, the most known receiver on Earth for those satellites is that dish. And you point it, whatever it is, it's an antenna, a receiver, but it needs to be pointed to receive that signal from that satellite. Remember, there are lots of satellites on this circle. There are thousands of them, sent by different countries, different companies, different transmissions, different radios, TV and all that. So you need to be pointing that at one particular satellite. You can change it to another satellite. So most these receivers, they're actually, they automated. They can have a motor on it and can change from one of these satellites to another. Of course, if you are on this side of Earth, on that side, then you cannot see the satellites on the opposite side, on the other side of Earth. And because, again, just because of the equator bit, remember, if this is Earth and this is the northern hemisphere and this is the South Pole and North Pole, and the equator is here, then all these satellites are based around this circle. Now, if you were in the north, like if we're here in Ireland or Sweden or somewhere, we'll be pointing your dishes southward to either somewhere here towards the east or pointing it somewhere towards the southwest to pick up your signal. And if we're in South Africa, you'll be pointing your dish upward because all satellites are at the equator. If you are right at the equator, what is India right at the equator? Does it pass through? Yeah. Okay, then you'd be probably most dishes would be pointing straight upward or either east or west. Maybe. Okay, so that's in general. And the satellite, because you're pointing at that satellite and your dish is pointing at it, it can't go, past it. And that's why it has to rotate and travel at exactly the same speed. So as Earth rotates, for example, here's the satellite, and I have a dish and I'm on Earth. As Earth rotates, this has to rotate exactly at the same rate. So in such a way that I don't have to move the dish. It's always pointing at it. So the satellite, compared to a point on Earth, it's fixed. It's relatively fixed, even though it's spinning at tremendous speed, but it has to be fixed. And if it changes, deviates a little bit, the signal will get weaker. So how do they do it? Is that they release, anytime they want to put a satellite, most stations that will launch a satellite on, put it on orbit, they launch their rockets from somewhere along the equator. The American NASA thing is there at the equator in California, I think, and whatever the French, they use one of the islands on the equator, and they start to, they're getting an approval. So the rocket leaves with the spaceship, and once it reaches a certain speed and the height, it releases it, and it just keeps spinning continuously. And it keeps spinning continuously for two reasons again. So every satellite that rotates, it gets kind of, it rotates at tremendous speed that everything that rotates generates, there's a natural thing again, like the resistance of electricity in wires or the radiation of electromagnetic field. Also mechanically, anything that spins, it generates a force to pull it away from the center. It's called centrifugal force. So this satellite will generate a force that will be pulling it away. In fact, will be pulled into that direction. But also gravity is pulling it back. And the combination of those two forces will cause it just to keep going in the same orbit. And the more it's going this direction, gravity will pull it away and keep rotating, and it will maintain its orbit. And that's the only orbit, that's the only distance. Remember, the further away from Earth you go, the weaker the gravity force. The speed has to be fixed because these need to rotate 1 revolution per day. But that speed will generate a certain force of centrifugal force. You need enough force to balance it, just to pull it, not to pull it too far and not too weak that it will pull itself away. So that gravity force, like here, the gravity force will be very strong. Here will be a little bit weaker, here much weaker. And that's they found that the best, the most suitable gravity force is at that distance, which is 365,000 kilometers. There are many other satellites that are on this side, that are closer to Earth. But because they are closer to Earth, gravity is much greater. In order for them to remain in this orbit, they must spin much faster. They must generate much stronger centrifugal force. And that means they must rotate much faster around Earth. And they do actually rotate around Earth 5 or 10 times a day. That's how fast they rotate, the closer upwards. But you cannot follow them up with a receiver. It doesn't work. You can't have a fixed receiver because they're going much faster than Earth is. But so what they do is they dump their information at certain points on Earth. Are they weather ones? I think they're more of a military satellites and more of spine satellites that they rotate. So in military, they use them a lot. They go and take a picture, they say, okay, they get the picture and say, we're gonna bomb that place. So they send the bombers, they bomb that place, and it comes back in 6 hours. You know, it rotates maybe over 4 hours. It comes back again, takes another picture, say, oh, we missed it, go back again, until they get so that's why militarily they're very handy, of course, but humanly they're not. But anyway, they're not ours, we will not be dealing with them. The only ones we deal with are the ones that are fixed as far as in relation to Earth, and they are at a certain point, and they are our communication satellite. Now, once they're put in there, every now and again, remember there's something else around Earth there, it's called the moon, and also the surface of Earth is not a smooth surface, and also it has a lot of big volume of water that keeps moving up and down, and it affects its gravity. So these devices, also sometimes the planets are lined up, but they have a gravity force that they can pull those satellites a little bit out of orbit. So every now and again, satellites move out of this orbit. When they move out of orbit, they're no good. So all the receivers are pointing at it in this location. If it moves there or down or anywhere else, it's useless. So they have an engine in every satellite, a rocket engine, that it can shoot its kind of force in either direction to bring it up into line up back into orbit. And so hopefully they remain in orbit, but sooner or later they'll run out of fuel. And the first few satellites that they placed up, first communication satellites, they had enough rocket fuel to last them for about 5 years. Nowadays, satellites, they can stay up for about 18 to 20 years. They have enough rocket fuel to keep them in the required orbit. But once the fuel is finished, then the satellite becomes uncontrollable. And it can either, if it kind of spins a little bit closer, then the gravity will keep pulling it, and it keeps spinning, and closer, the gravity gets stronger and stronger. Eventually it will pull it, and it will crash onto Earth. And we had a couple of them maybe that crashed the last 10 years. Luckily, they've crashed on oceans, because these satellites are quite large pieces of equipment, like a double-decker bus. They're quite large and heavy. And they come spinning at tremendous speed. Like if they fall in a city or a house, they would definitely destroy it. They cause some chaos. Okay, so that's how they work. But how do they actually operate? That's fine, as I said. A television sends a signal upward, or a sender sends the signal, and the signal is transferred back. And it covers a larger surface of the Earth. So if we want to broadcast, then satellites are suitable. So this is another question when selecting the property, which one would be a suitable medium? And we talked about twisted pair, and we talked about fiber optic. Now also mentioned satellites. Satellites are more suited if you have broadcasting. So are you gonna for broadcast? All broadcast is either point to point or multi-point. If you're going for point to point, maybe a fiber optic is better. But if you want to broadcast, let's say you say we want to transmit a television channel to London. You're not gonna lay down cables. It'll take you, years. So a satellite is great. And also setup time. The point is, satellites are plenty of them, they're there and they're available. So if you if for example you decide, okay, next week we need to go to Morocco and start some activity there and want it to be broadcasted. Well, you need to go down to Morocco and dig the cables and prepare the network there. Especially military operations. You want to go to Morocco, maybe invade the country. Your military land there, they need to communicate. You need a network. So you can go down and take you 6 months to lay down cables and connect everybody, or else satellites, in 24 hours, you can actually set up your transmission. So if you have the money, and if you want, you can book a channel tomorrow to transmit on any satellite, well, not any satellite, but whatever satellites that are available for a particular area you want. So setup time is very, very short on satellites. If you need to build up a network of twisted pairs or fiber optic cables, it can take you a lot longer. Like the satellite can be as short as 24 hours, you can start transmitting. Broadcast, all the cables are point to point. Any cable is point to point. Okay, even if you have a local area network, you want to broadcast to them, yeah, but every device has to be connected separately by a separate piece of cable with a long or short distance. And we know fiber optic cables can travel a long way before requiring a repeater, but satellites can travel even longer. Like satellites, you can go thousands of kilometers. So the question sometimes comes up, all right, we have an office down in the country. Is it better to lay down a cable or we use a satellite? Maybe you go some research area in the desert or somewhere. All right, you can lay down a cable between our two stations. Or we can use satellite. Which one is better? Which one is cheaper as well? So from a cost point of view, there's a general figure, 500 kilometers. If you have flat, easy area to lay down cable, like cable usually you need to dig a small tunnel and lay down the cable, cover it. But still cost money and time, or you use a satellite. Satellites are not so cheap, so you have to pay for it. So sometimes, in the general, longer distances will be cheaper to use satellites, shorter distances will be cheaper to go for cables. But what's the limit? They say around 500 kilometers. So if a flat land, no problems, no mountains, nothing, at 500 kilometers or less, cable, twisted pair is probably cheaper to lay it down and leave it. Lifetime. Which one has the longest lifetime or shortest or whatever? Fiber optic or twisted pair or satellite. Okay, so what's the lifespan of a satellite? Any idea? Satellites? What's the satellite lifespan? Satellites have the maximum limit that's imposed by the rocket fuel they carry, usually 18 years.
But the ones that are at 365
yeah,
they don't have the fuel. They say it's stationary.
they do. But they always, every satellite you put in orbit, it can be occasionally affected. and it can out of orbit, and it needs to be corrected. It's not the rocket isn't always working. It's the engine is there. Every now and again, it's like, yeah, it's like some people they put compressed air and they just blow it this way and it brings the satellite back. But as far you know what the textbooks say, they use actually rocket fuel. It's a fuel that blows it in the opposite direction. Keep it in line, keep it in order. But sooner or later, that rocket fuel runs out. That fuel runs out. And for now, maybe in the future they find a better way of keeping it in orbit. But for now, they are limited. And there are so many, there are thousands of satellites that are under, they lost their control. They have no fuel to keep them in orbit. They're just spinning away. Some of them are getting closer, some of them further, some of them, they're just dangerous. And they are causing a problem now in space for other, astronauts and other spaceships and all that. And they're thinking of ways how to, maybe one of you can come up with an idea, but they blew them up sometimes. They opened up one and blew it up. And by blowing it up, instead of getting rid of it, instead of one big satellite spinning at a few thousand kilometers an hour, now they have a million smaller pieces spinning at the same thing, and that can be dangerous as well. If they come towards Earth, they might burn along the way in the atmosphere, but they still make it to Earth because they have a large mass. Anyway, so these are the actual media that you need to know. What time is it now? How are we doing on time, guys?
What was your conclusion on the distance? The time they can stay?
Satellites have a time
It's higher than fiber
about
optic.
18 years. Or
Okay,
so.
so fiber optic would be the better.
Yeah, fiber optic has no time limit so far. We don't know it. It's just like CDs. When CDs came out, the manufacturers said they'll never run out. They're there. You burn the information onto them, and they'll stay forever. Unfortunately, I found that they did not stay forever because that material that burns, that they burn, the metal that they burn on the CD, is actually consists of few materials, few metals. And there's another natural thing. Nature has so many things. Another natural thing is that if you mix different metals together, or they touch, even if they touch one another, they corrode after a while, after a few years. They cause corrosion and they rust away. Yeah. Twisted pair. If it's exposed to humidity, they'll disappear within months. Like if salt, within weeks. So if they're kept in very dry and good environment, they probably last for decades. We don't know. I don't quite know. All right, okay, quick thing. Which one is better, a satellite or a fiber optic cable?
For what?
Yeah, exactly, for what? You tell me for this reason, satellite is better, or fiber optic cable is better.
Less expensive, but more secure.
Okay, fiber optic cable is more secure. Okay, now a couple of other points. Satellites, when they send a signal, it can be affected because they send a radio signal. A radio signal is an electromagnetic signal. And if while coming down to the receiver, passes through these clouds, and there happen to be a storm, and electric storms up in the sky, they are electric. And this signal that comes, it's an electromagnetic, so the magnetism in it is messed up. So you can actually have a problem with receiving a signal. Fiber optic, so far, its signal is quite uninterruptible or pure. There's no direct interruption so far unless something goes wrong. Which one? More ideas come up, but I forget them by the time I finish them. Right, so yeah, you have a question or you want to answer?
No, I have a question. Say if fiber optic cable is more expensive to replace than anything else,
automatic satellites, obviously.
Yeah, it is, yeah. You cannot fix it in situ. You must fix the entire piece of cable. It's manufactured, it's easy to manufacture it in a factory under certain environment where it gets one length of that wire. But once that wire breaks, there's no way now of melting it and bringing it back into the exact shape that it will continue to transmit the signal. So far, not in situ, it cannot be repaired in situ.
You didn't know anything and you just.
Right. Media in general, it's known as guided media or unguided media. The guided media is anything that flows through a wire. The wire guides it to a certain point. The unguided generally refers to the wireless media. And the cables, there are a number of cables. We talked about the twisted pair and the fiber optic cable. The twisted pair is twisted for two reasons. Why don't they just have a pair of wires going from one machine to another? One is twist and the name is twisted. Because something else that has twisted pairs have a problem with, and that's catching noise. Noise goes into them. It's generated by the magnetic field of other devices. So if a cable goes beside an air conditioning unit, every time the air conditioning unit is switched on, it generates a magnetic field. If that wire is in the magnetic field, in the vicinity of the magnetic field, it will generate a current inside it. That current will cause noise, and unrecognizable original signal becomes unrecognizable. They call this noise. So to reduce that noise, why does a wire pick a signal? It has to be a straight wire, like the antenna of a radio. Like if you have a car and you have the antenna, straight wire, it receives the electromagnetic signal in the air and generates a small current that goes through the antenna into the radio that amplifies it and plays it for you, and the audio comes out. A bad antenna is an antenna that's not straight. If your TV or radio antenna is not straight, it's a bad antenna. And hence, they twisted those wires to make sure, but to ensure that they're not a good receivers of noise, of magnetic signal. And that's one reason. And the other reason is that if you get noise on one side of the circuit, once one side receives more noise than the other, it's more difficult to deal with it. So it's better to deal with the noise if it's spread on both sides. So on both sides, this is if the source of the noise is closer to one of the wires, it will generate more noise on one of them than the other. If they are twisted, then probably the noise will affect both wires, because it will be kind of in contact with both wires and probably generates equal or balanced noise on both sides, and that's probably easier to deal with. The network cables are it's sold in pairs of cables, and some of them are to reduce radiation or reduce being affected by noise, by other magnetism. They might cover them with metallic material that can absorb or hold their radiation or prevent the outside effect on them. It doesn't fully do the job, but it's better. And they're called shielded twisted pair of wires or unshielded. Of course, the shielded are more expensive and the unshielded are cheaper. This is really what Cat 5 look like. And this is the kind of terminator that goes onto the end of those wires. If we get a chance, you should have done some sort of cable manufacturing. Have you all made some network cables? I'll try and bring it, if we can get, we have some stuff in the faculty, if we can get the terminators and the cables, we'll bring them up. These are the different categories that are available, that's like up until the notes were written, so it's category 6, so now I hear there's category 7 is already out, so hopefully it can have bigger range and it can carry more information. Right, the next cable is a coaxial cable, we won't talk about it, but it looks like the TV antenna wire. It used to be one of the major cables used on local area networks. It's no longer in use in most networks. It's slightly thicker and it has different terminators. This is the fiber optic cable, and the way light travels through the wire with light generator from one end and the other end back converter into an electric signal. The angle that the light falls onto the glass can either cause the signal, the light signal, to go through or reflects back. So it either reflects or refracts. Reflecting is staying within the same tube or a glass of pair of glass. Refracting is getting out. So the signal, the bigger the angle, the more likely then the ray of light will remain in there. So they've measured it, and most of the time you need to be pointing it at that wire. The way it's connected, the angle is never gonna go anywhere that it's large enough to be refracted. You get in there.
What's the attenuation due to in fiber optic? The attenuation, what is it caused by in fiber optic?
What is it caused by?
Yeah.
It's just the light signal loses the energy of traveling. You put certain frequency, I don't know, by the glass itself, I guess, by the medium that's carrying it. We normally, these people who look at fiber optics or who manufacture them and design, they do electrical and electronic engineering, and it's a different specialty. But it's probably it's probably here to stay. Fiber optics are here to stay. So that's what fiber optic might look like. These are the kind of multiplexers that you can get. So instead of not knowing that how much your network is going to grow and you cannot do any tapping, this provides tapping already. Twisted pair has a number of advantages and disadvantages, so you should look through them. They're easy to work with, easy to tap. Watch the tap can be an advantage, can be a disadvantage. Easy to twist into tight corners. So if you decide to use fiber optic cable and you have to twist the cable around a 90-degree angle, it will break. Glass wire is very fragile. They cover it with some material to give it a bit of support or strength, but if you try to force it to twist it, anytime you want to twist it, you have to put it in a radius, in a circle, so it doesn't bend, it doesn't break. Twisted pair is full duplex. Anybody remembers what full duplex is? Simplex communication. Do you know what simplex communication? Half duplex. Did you do any networks, guys? Like, this is basic stuff. Okay, and we don't have time, so I'll just. Full duplex, you can use the same wire to carry information that way or this way. You can communicate in both directions. Twisted pair, you can use it for that reason. Half duplex is you can communicate in both directions, but not at the same time. You either send or you receive. And then when you finish, you can send. And then you finish, you can send. You can send in both directions, but not simultaneously. And simplex communication is only communication in one direction. So if you listen to your radio in the car, the transmission, the radio station is sending it to your radio. Your radio never sends a signal up to the station. We call that simplex communication. So simplex is communication that only happens in one direction, never in the opposite direction. But twisted pair have problems. That's security problems. It radiates and therefore it's not secure. It's easy to tap and therefore it's not secure. It's low bandwidth. It rusts away with salt and humidity. It's prone to be affected by noise, electromagnetic noise. If there is an electromagnetic in the vicinity, it has low bandwidth, it's already written there, and it's very heavy in weight. So if you have to maybe lay down 100 kilometers of cables, if you have to carry twisted pair, you need heavy equipment, big trucks to carry it. They're heavy. Kind of small amount, you carry a small cable or rope, it can be heavy enough, but with longer distances or longer cables, they can be very heavy compared to fiber optic cables. So fiber optic cable is much lighter to carry and handle, but it's more sensitive. Satellites. This is the noise where it can be affected there by noise in the storm. So if a signal coming from a satellite passes through a storm, it'll also the rain actually affects satellite transmission. So if you're watching a TV using a dish or using a satellite, and if the weather is raining outside, most likely you'll get noise. The distance is 35,780 kilometers of those where satellites are from the surface of the Earth. The satellite is always fixed in relation to any point on the surface of Earth.
The closer ones we were talking about, the military ones, or is that the farthest one?
This is the communication one. The military ones will be here, closer, a lot closer than the 35,780 kilometers. And they rotate at much faster rate.